All right, what's up, YouTube? This is my first fucking live stream. We're just chilling here. At the cafe. And we're about to have an interesting show today. So basically, what I'm going to be reading today is the article released by Scientific American, titled "Big Cosmological Problems," as well as a new gravity experiment that was just done about a week ago, and we're gonna take a look at it and give our thoughts and opinions. So let's start with the big cosmological problems article. There we go. So we're gonna read this. So, title: Cosmology has some big problems. They could not have said it better. Okay. And so, the article starts by saying, what do we really know about our universe? Born out of a cosmic explosion 13.8 billion years ago, the universe rapidly inflated and then cooled. It is still expanding at an increasing rate and mostly made up of unknown dark matter and dark energy, right? This well-known story is usually taken as a self-evident scientific fact, despite the relative lack of empirical evidence and despite a steady crop of discrepancies arising with observations of the distant universe. In recent months, new measurements of the Hubble constant, the rate of universal expansion, suggested major differences between two independent methods of calculation. Discrepancies on the expansion rate have huge implications, not simply for calculation, but for the validity of cosmology's current standard model at the extreme scales of the cosmos. Another recent probe found galaxies inconsistent with the theory of dark matter, which posits this hypothetical substance to be everywhere. Yes, I mean, they say, I think, like 99% of our universe is made up of this untestable, unfindable matter and shit. So let's keep going. But according to the latest measurements, it is not suggesting the theory needs to be re-examined. It's perhaps worth stopping to ask why astrophysicists hypothesize dark matter to be everywhere in the universe. The answer lies in a peculiar feature of cosmological physics that is not often remarked. For a crucial function of theories such as dark matter, dark energy, and inflation, which each in its own way is tied to the Big Bang paradigm, it is not to describe known empirical phenomena, but rather to maintain the mathematical coherence of the framework itself while accounting for discrepant observations. They're basically saying, and Nikola Tesla said it himself, science today has gone so far from being real observations and things like that, where we're really just relying on mathematical equations which do not tell us the reality. It simply does not. Fundamentally, they are names for something that must exist insofar as the framework is assumed to be universally valid. Assumed. Each new discrepancy between observation and theory can, of course, in and of itself, be considered an exciting promise of more research, a progressive refinement towards the truth. But when it adds up, it could also suggest a more confounding problem that is not resolved by tweaking parameters or adding new variables. Consider the context of the problem and its history. A mathematically driven science, cosmological physics is usually thought to be extremely precise. But the cosmos is unlike any scientific subject matter on Earth. A theory of the entire universe, based on our own tiny neighborhood, as the only known sample of it, requires a lot of simplifying assumptions, When these assumptions are multiplied and stretched across vast distances, the potential for error increases. And this is further compounded by our very limited means of testing. Thank you, somebody, for finally fucking saying it. Whew. Man, this is refreshing to read, man. Scientific community actually realizing some shit here. Historically, Newton's physical laws made up a theoretical framework that worked for our own solar system with remarkable precision. Both Uranus and Neptune, for example, were discovered through predictions based on Newton's model. But as the scales grew larger, its validity proved limited. Einstein's general relativity framework provided an extended and more precise reach beyond the furthest reaches of our own galaxy. But just how far could it go? The Big Bang paradigm that emerged in the mid-20th century effectively stretches the model's validity to a kind of infinity, defined either as the boundary of the radius of the universe, calculated at 46 billion light years, or in terms of the beginning of time. This giant stretch is based on a few concrete discoveries, such as Edwin Hubble's observations that the universe appears to be expanding, and the detection of the microwave background radiation. Okay. But considering the scale involved, these limited observations have had an outsized influence on cosmological theory. It is, of course, entirely plausible that the validity of general relativity breaks down much closer to our own home than at the edge of the hypothetical end of the universe. And if that were the case, today's multi-layered theoretical edifice of the Big Bang paradigm would turn out to be a confusing mix of fictional beasts invented to uphold the model along with empirically valid variables, mutually reliant on each other to the point of making it impossible to sort science from fiction. You know, somebody needs to really go on Scientific American, type up this article and read it for yourself, because I am not lying. This is what the fuck they're saying. And so this is straight off the article. Compounding this problem, most observations of the universe occur experimentally and indirectly. Today's space telescopes provide no direct view of anything. They produce measurements through an interplay of theoretical predictions and pliable parameters, in which the model is involved every step of the way. The framework literally frames the problem. It determines where and how to observe. And so, despite the advanced technologies and methods involved, the profound limitations to the endeavor also increase the risk of being led astray by the kind of assumptions that cannot be calculated. After spending many years researching the foundations of cosmological physics from a philosophy of science perspective, I have not been surprised to hear some scientists openly talking about a crisis in cosmology. In the big inflation debate in Scientific American a few years ago, a key piece of the Big Bang paradigm was criticized by one of the theory's original proponents for having become indefensible as a scientific theory. Whoa, interesting. Why? You ask? Because inflation theory relies on ad hoc contrivances to accommodate almost any data. And because its proposed physical field is not based on anything with empirical justification, this is probably because a crucial function of inflation is to bridge the transition from an unknowable Big Bang to a physics we can recognize today. So, is it science or a convenient invention? To me, a convenient invention. I didn't say that last part, I just put it in there, but you know, it is a convenient invention. A few astrophysicists, such as Michael J. Disney, have criticized the Big Bang paradigm for its lack of demonstrated certainties. In his analysis, the theoretical framework has far fewer certain observations than free parameters to tweak them. a so-called negative significance that would be an alarming sign for any science. As Disney writes in American Scientist, a skeptic is entitled to feel that a negative significance after so much time, effort, and trimming is nothing more than one would expect of a folk tale constantly re-edited to fit inconvenient new observations. Sir, props. 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 That's all I have to say. As I discuss in my book, Metaphysical Experiments, there is a deeper history behind the current problems. The Big Bang hypothesis itself originally emerged as an indirect consequence of general relativity, undergoing remodeling. Einstein had made a fundamental assumption about the universe, that it was static in both space and time. And to make his equations add up, he added a cosmological constant, for which he freely admitted there was no physical justification. But when Hubble observed that the universe was expanding and Einstein's solution no longer seemed to make sense, some mathematical physicists tried to change a fundamental assumption of the model, that the universe was the same in all spatial directions but variant in time. Not insignificantly, this theory came with a very promising upside: a possible merger between cosmology and nuclear physics. Could the brave new model of the atom also explain our universe? From the outset, the theory only spoke to the immediate aftermath of an explicitly hypothetical event, whose principal function was as a limit condition, the point at which the theory breaks down. The Big Bang theory says nothing about the Big Bang. It is rather a possible hypothetical premise for resolving general relativity. On top of this undemonstrable, but very productive hypothesis, floor upon floor has been added intact, with vastly extended scales and new discrepancies. Excuse me. To explain observations of galaxies inconsistent with general relativity, the existence of dark matter was posited as an unknown and invisible form of matter, calculated to make up more than a quarter of all mass, energy content in the universe, assuming, of course, the framework is universally valid. In 1998, when a set of supernova measurements of accelerating galaxies seemed at odds with the framework, a new theory emerged for a mysterious force called dark energy, calculated to fill circa 70% of the mass energy of the universe. The crux of today's cosmological paradigm is that in order to maintain a mathematically unified theory valid for the entire universe, we must accept that 95% of our cosmos is furnished by completely unknown elements and forces for which we have no empirical evidence whatsoever. For scientists to be confident in this picture requires an exceptional faith. And I fucking emphasize faith in the power of mathematical unification. In the end, the conundrum for cosmology is its reliance on the framework as a necessary presupposition for conducting research. For lack of a clear alternative, as astrophysicist Disney also notes, it is, in a sense, stuck with the paradigm. It seems more pragmatic to add new theoretical floors than to rethink the fundamentals. Contrary to the scientific ideal of getting progressively closer to the truth. I couldn't have said it better. It looks rather like cosmology, to borrow a term from technology studies, has become path-dependent, over-determined by the implications of its past inventions. This article is based on edited excerpts from the book Metaphysical Experiments, Physics and the Invention of the Universe, published by University of Minnesota Press. The article is by John Eckenberg. He is a PhD philosopher of science and the author of that book. So, yeah. What do you guys think, man? Let me know. I mean, I love how before you even read the article, they have an image of the just a stunning CGI image of the galaxies right here. Amazing what computers can do nowadays. But let's go look at this. I mean, we just read what that was. I mean, honestly, I do not think it could be professionally said better than that. I mean, really, that was amazing. That was kind of breathtaking, honestly, to hear that directly from the scientific community in an article released to the masses saying that. Whoa, that's a big step in the right direction, man. Fucking what's his name? Chris Kringle, man. One foot in front of the other. Pretty soon we'll be walking out the door here, you know? But let's look at this yes, so Epic Gravity Experiment is the name of the video, and it's by J. Tolan Media 1. And I'll read the description of the video. The gravity model is put to the test. Will it hold up? This is how it works. I align the telescope's optical axis to the same distant target from a few locations, varying in horizontal distance from the target by slightly over 1 mile. The target is a tower at 54 miles average distance. The elevation angle of the optical axis of the telescope is measured with a high accuracy inclinometer. The experiment is designed and the locations chosen to produce results outside the measurement error bounds. Gravity is a vector field, meaning it has a magnitude and direction. Here, we try to measure and determine if the gravity vector direction is changing with distance, because the current theory says that it should. It diverges away from the center of the planet. So, gravity experiment. The video will be done by a guy named J. Tolan Media, and check out the experiment. Take some notes. I think it was quite amazing. The data shown is truly breathtaking, and especially compared to when he really starts talking about if we were to really upscale the experiment and give a greater distance. I mean, it would only be even more breathtaking because I mean, what the data shows in the experiment is quite convincing. But yeah, amazing things, guys. Amazing things going on in flat Earth. I'm so blessed to be in a time where I can even have this belief and express it with people. I'd like to think, when I do my activism, people always ask me, what's your grand goal? And I mean, I have a bunch of responses for that. But ideally, the grand goal is to end human slavery. And many people will be like, think about it logically. Well, like the government has so much of a control. How can you even ever do that? And that's very true. The government does have control, but we can't be defeatists. I like what Flat Earth Fokker said about that. He was like, man, you can't be a fucking defeatist. You have to have some faith. I think God is bigger than all of this. So, I mean, hey, I have faith that anything could happen at any moment. So, I'm probably going to go do some activism right now. Stay tuned. It probably won't be live because YouTube won't let me go live on my phone. If anybody knows why, please feel free to let me know so I can do something about that. But thank you guys for tuning in. I didn't have any live viewers this time, but hopefully I'll find a way to get into doing it live, and so I can have you guys right here with me while I'm doing it. But thank you. I appreciate it. Have a good day. And go check out that article and experiment, everyone. Thank you.